robust 3D object reconstruction. The speaker is Thomas. Now it's your time.
Okay, well, good morning, everyone. I'm presenting the research of our group on 3D object reconstruction based on Monocular SLAM and CNN Semantic Segmentation. My name is Thomas Weber. I'm from the Reconstruction University in Germany. Yeah, let's start. So a quick reminder of what is LSD SLAM. LSD SLAM was developed on the Technical University in Munich, and it's large-scale direct SLAM. So it basically takes a grayscale image, generates feature points based on gradients in this image, and tries to match these feature points in a keyframe to the next keyframe. And based on that, it estimates the distance of these points in 3D space and the camera in the scene. So this is what we are building on. Our work mainly revolves around our industrial partners, and they are interested in gripping things, basically grasping outer spins, and general manipulation tasks. So in our research, we use parts like these. These are some industrial parts for assembly of these aluminum profiles. You might know these item profiles. So the cool thing about these is we also have the 3D models of these. So this is very helpful for the next few steps in our research. So by using LSD SLAM, we can generate a point cloud like this, where we just have the point cloud with the objects in there. I mean, you can see them as human, but the machine cannot see them, right? It's just points. So who would it know what points belong to what object? So this is not very helpful. If you want to grasp the object, you would ideally have point clouds that are separated. So in these point clouds, you can also align the 3D model of the object, you already know, and you would have ideal grasping positions. Because if you have the model, you have the points predefined, so you know everything, right? So I will show you a quick demo of the running setup here. You can see the image on the top right. On the bottom left, you see the generated keyframes. And on the right side, you can see the SLAM viewer. So it's basically the running LSD SLAM. Yeah, it happily generates a point cloud here. And yeah, the interesting, no, we have to finish point cloud, but we have to extract the individual part point clouds out of these. So our approach is by doing a semantic labeling on the RGB image with the CNN network. And this allows us to just select the points out of the point cloud that belong to the objects we are interested in. So you can see like the keyframe is on the left, on the right you have the labeled image, and I color-coded the objects there. And this allows us to extract these single point clouds out of the image based on what object we are interested in this point cloud. There's like from another keyframe, another labeled keyframe, and some other point clouds. And here you can see the actual 3D models. They are registered and scaled in these point clouds. So the accuracy of the reconstruction is pretty good, and also the alignment of the 3D model in this point cloud we are looking for. As you can see here, the point cloud is very close to the object, so there's not a lot of deviation here, except for these few strong points that are based on the cutting out of the image, like just from the custom of the camera, they got selected. Yeah, so for the CNN segmentation, you need data, obviously. And the good thing is, since we have the 3D models, we can generate training data how we want it, right? We have open source software. I use Blender. You may know these 3D creation suites. You could use anything that allows some physically based rendering. So we generate all these images, and we can generate different lighting conditions, different focus of the camera. We can unsharp focus, whatever, different backgrounds, what do we want, right? So if we notice semantic segmentation of the CNN network is not great in these few spots here, we can just generate more training data for these special cases there. And this is on mask RCNN, so you can see we get for the objects the individual instances, and not just the semantic label overall, but the individual parts and also the individual group keyframe of the LSD slam to just apply the labeling there. And this is shown in this graph. So you have the LSD slam running on the top. It generates the keyframes. On the left-hand side, it just does its normal thing, where it estimates the camera pose and the depth of the points. And we do the semantic segmentation on the RGB input. And once we get the keyframe point cloud, we just overlay them with the RGB image that's labeled from CNN and just cut the point cloud based on this. So as you can see, image A is the grayscale input. In B, you can see the labels from CNN, and image C, there's an overlay. And in D, you can see the point cloud cut based on these overlays. So this is the bottom row. You can see the individual point clouds there. This is not very great because you still use all of the image information, right? So if something in the background changes, this might screw up the LSD slam and distort the point cloud from the next keyframe to the successive keyframes there. So what you really want to have is just the object you are interested on, right? So basically maybe just the green object, right? You just want these points, and ideally you just want to create these points. So you kind of cut out all the background noise there. So this is what our second approach suggests. So here we do manipulation on the input image for the LSD slam core. So we take the RGB image, make a grayscale out of this, and on the RGB image we also do the semantic segmentation. And once we get the labels there and the masks, we use these masks to actually just cut this part of the image and feed this part of the image to the LSD slam. You can see in image A again, we have the normal full image, and we just focus on this yellow rectangle, the angle bracket there. We do the semantic segmentation, we get the mask, and now in image C, this is the mask from semantic segmentation. And because LSD slam works on gradients, it generates the key points, feature points for the keyframes. We have to blur the mask out a bit. So on sharp edges, we would generate lots of keys, lots of feature points, and that's not really helpful because we want actually the feature points that are from the object there. So this is why you see in image E, it's overlaid the blurred mask on the image A. Image F is actually then the resulting feature points LSD slam detects on this input frame. And you can see in picture G, we actually only have a 3D point cloud now of this object. Right? There's no noise. The complete background, everything that's not belonging to this object is just cut out. And this is great if you have things moving in the background, right? Or if you have other objects in the background that change via two of these keyframes. So you have still a stable point cloud on this one object because all of the keyframes, we force them onto this object. This is also shown the results here in the first table. You can see performance based on method 1, right, where we take the finished keyframe and just apply it there. So obviously we generate fewer feature points, right, because we only use the small part of the image where the object is we are interested in. But the interesting part is also in the third column there, in the post table, third row, sorry. We generate much more keyframes, right? And more keyframes means more updates to the point cloud. So it's a more detailed point cloud, basically. And this is because now that we only have this small part of the image, a small shift in the camera position will make a huge difference for the algorithm there and generate a new keyframe. Then a second table, you see basically the normalized errors of the point cloud we align to the 3D model stays roughly the same. Right, so there's not much change there. But the interesting part is down in the third table, where you see in method 2, we basically have less noise because the standard deviation is basically cut in half. Right, so the point cloud generated is less noisy. So this means you get a better result there. So in conclusion, both of these methods yield a separated point cloud. Right, method 1 is the CNN masking applied after the keyframe generation, but this is slower than method 2 because you still use the whole frame, right? You have to generate all these feature points in all of the grayscale image, and this takes time. So this might be better for applications where you expect a stable scene with no change in the background or no moving parts, because as I explained, moving parts will influence the LSD algorithm. The accuracy may be lower there, because you still have the background in there, and this might mess up your generated point clouds. In method 2, we basically cut out all the background there, so this should be more robust to any motion in the background or basically dynamic environment in the background. Yeah, basically all the feature points are concentrated on this one object, and basically everything else is filtered out, so the background noise. Keyframes are generated at a higher rate there, because we just force them on this object, and slight changes there make a huge difference and generate a new keyframe. Yeah, and as I already said, this might be better for dynamic environments or also non-rigid environments, because you only have this one object and only generate a point cloud from this one object of the image. So thank you so far. Are there any questions?
Let's take some questions. Any questions?
Thank you a lot for your talk. I have a small question about the errors. I don't remember, did you mean it, but what errors do you use for?
Yeah, we use the 3D mesh of the point cloud, of the object, right, and the point, basically the error of the point to the mesh, right, so the distance of the point to the mesh of the 3D object.
Any other questions?
It's just a technical question. So you have the shiny metal parts. What kind of sensor do you use there? And do you have any problems with this type of objects?
Yeah, the sensor is just a monocular RGB camera, right? So there's no special sensors. It's basically your smartphone camera. And these parts we use, they are not high polished, right? They have some kind of matte finish, or they might oxidate over time. So they are not really that reflective. Right? If you have really reflective parts, that might obviously be problematic, because things reflecting in there generate also feature points, but it's not actually in the object, but in reflection somewhere else in the world.
Any other questions? Okay, one more.
So hi, great talk. Apart from the actual point cloud extraction, do you get SE3 information of the actual point cloud?
Sorry, what?
The actual model, do you get it? Do you get the actual orientation information or position orientation information?
Yeah, it estimates also the camera position, and once you register the 3D model in there, you know how the 3D model is aligned to the camera. So you have basically full alignment and orientation.
Okay, thank you very much. So now let's thank our speaker. We will move on to the next session.
Yes, so now becomes the interesting part, the poster teasers. So what we do, all the poster presenters of poster session 1, so the regular posters should come down